So, so it's going to be an interactive course. I also have to assure that whomever really wants to learn will learn. And that is a challenge because it is my experience that if we take the intersection of what you know, it's going to be an empty set. Doesn't mean that an individual person doesn't know things, but intersection is going to be relatively small. I cannot assume even that people know how to program, in C++, because some of you guys write Java. This is perfectly fine. I cannot assume that those of you who program in C++ actually know C++. From the, at least, it's often my impression when I read the code. Dima, there is a place. Slava? Fine, go. I also will try to learn all of your names, because I don't want to say, oh, you in the green shirt. It's not going to be productive, but it will take me a while, in any case, I printed all your mug photographs and studying them very carefully, so eventually I'll get it. Of course, I hope that by the time I learn them, there will be just 5 people left. And so, okay. So you have to be very patient with me because, first of all, I'm going to be writing code in front of a big audience. And for those of you who try doing it, it's difficult, everything is going to be wrong. It will never compile. It will, but it's just, I think it would be so much better. So we had to start with a very, very simple program. Most of you recognize it, right? Hello world. So I wrote it, and the person here said, well, but it's not going to compile, said he. Let us try. By the way, why do you think he says it's not going to compile? He says there is no return value. We promise. It's like int main, right? So main should return something in integer. And apparently we're not returning anything. So the person in question sits here with a smug expression on his face. I'm not going to tell you who he is, but let us go and test whether he is right. I don't know. I haven't tested it before. I promise. So we say G++, day 1 CPP. It did compile. All right? So, okay, let us think about it. What is it? Is G++ not doing the right thing?
Is it returning the value of std : CF?
No, it's not. Let us see it has nothing to do with that, because let us put something. This is C, so we could write 2 + 9 semicolon. That's a valid C code, right? So it will not change the behavior. I could do it, but let us seriously think about it. So if this function was called foo, would my friend be right or wrong? He will be right. So main is a special function. That's what we just discovered, that C++ treats main as a special function, which when you fall through, meaning when the control goes through the last brace, do you see the last brace? Something is returned. What is returned? 0. Because again, the standard Unix convention, which became universal convention right now, that on success you return 0. Right? So, yes?
Technically, you don't need to return from functions as long as you don't call them.
Well, yes, and technically you don't need to return from them as long as you you don't compile them. So, in most C++ compilers will at least issue a warning. Let us test it. Let us see a function called foo, int foo, int foo. It's very nice. When you try things like that, you could call your functions foo, but only in cases like that. So that, according to you, should be correct. Let us see what we get. What did I do? I don't know what I did. It does compile, you're right. And if we put it here, foo. Anybody wants to make a guess? Will compile? Does compile.
Try optimization lower, it might fail.
That is interesting. That I didn't know. Yes. This is a mystery. I actually have no answer. Yes.
Can you try with the lower optimization?
Lower. This is lower optimization. It defaults to O2, you think? I think it will not matter at all, but let us see. So you say, if I say O0, sorry. If what warning do you get?
Dash big W, then small bold. Then for the first case, I get warning control reaches end of non-void.
I see. Okay. G++ minus, this is very good. So tell me, capital W all J1 like that, yes? Of non-void function. In function. Okay. So in general, yes. So we figured out at least something now. So apparently it does detect it in foo and issues a warning. It did not issue a warning for main because this is a property of the language. The language actually allows you to do things like that. So again, remember we started with performance, and this all talk about performance started with Ryan and me investigating, very long queries. And we found indeed very, very long queries. So, and when we narrowed things, we always found something pertaining to incorrect use of STL. It's usually one-liner. And the most egregious, the most amazing thing is the following one-liner, which I will start in the beginning of the course because it was just so important that we could weave the whole fabric of the course around this one little example. We could start from this example. So somebody wanted to find out, there was a range of integers, and let us assume that they're called int, or what are uint32? Okay, let's call them int for the time being. Eventually we will extend them to other types. A bunch of integers, and the person wanted to find out how many of these integers are unique. That's a legitimate case. You know, if you need to find out how many of them are unique, you try to write some code. And the person sort of, let us assume that the person had some array int a with some integers. 1, 3, 1, 4, 1, 5. Of course, you say, well, he could have counted, but you know, it was a big array. So there was an array of integers. And the person decided that the way they're going to find out how many unique guys are there, they will write the following code. They'll say std, colon, colon. By the way, everybody knows this cout stuff? I don't need to explain how it works. Okay? It works the way you think it works. In any case. But, however, one warning. A friend of mine was writing cout thing, and he wrote something like that. He wrote cout some function call, and then cout some other function call. And lo and behold, depending on the compiler, different results were printed. Anybody could guess what happened? The order of evaluation, yes. What is wrong with order evaluation? The order of evaluation of arguments to a function is not defined, it's undefined. And what is this operator less less? It's just a function call. That is something to remember. You never depend on the arguments to a function being evaluated in a given order, because they will not be the moment you change the compilers or the moment you get to a new release of the compiler, as it happened in this particular case. Okay? The person in question actually immediately declared that he found a compiler bug. You know, again, all my life I hear, oh, you know, I found a compiler bug. The assumption typically is that it's your bug. It's not, I mean, compilers do have bugs, but they are not as common as people believe. So that's the important thing about less less. It is just, it's not some special form. For those of you who remember Lisp, there was a notion of special form thing, which it is just a function call. It's called to an operator less less. So the person did the following very clever thing. The person said std set, because the standard provides us with a thing called set. So the person said, let me create set int, and let me even call it set. Right? And the person is actually exceptionally good STL programmer, one of the two in the building. So the person correctly said, I could do the following thing. I could construct that set out of A, and we will discuss it in a second. And right now we'll just say A plus 6. Do you see why we need to discuss it? Why do you think it's a bad thing to put 6 there? Anybody knows what I really should do? Yes, because we really want the next time when somebody put a couple of more integers in there, we want this 6 to become whatever it's supposed to be, 8, I guess, right? So, but let's not address that. So this is a perfectly good thing. It works. Yes. Provided that we include set. So there are at least 3 people who know C++. Yeah. Yes. Include angle bracket set. Yeah. Guys, I apologize. You will have to see somebody embarrass himself all the time. So, by the way, we can get rid of foo. Our foo investigations are complete. So, we created that, and then we sort of want to find out how many unique integers there are, right? So we say std cout set of ints dot size, right? That should work. Every container in STL, as we will learn later, has size. That's how many things are there. So how many things in this set? And then std : end of line. Do you think it will compile? Not with a colon. Oh. You guys are so strict. So let us see if it's still, no. Up arrow twice, you think will work? No. No, not with I mean, I'm an Emacs. Yes. Okay, it did work. So let us try running it. A dot out. 4. It did work. So ship it. And you did. What's wrong? What is wrong with this thing? I mean, it's obviously compiles. It computed the thing. What is the algorithm for set? I could tell you. It's red-black tree, which is universally stated in every book to be one of the best implementation of sets. Textbooks, we have to believe what's written. Do we have to believe textbooks? We will see. But in any case, when we, very soon, will learn to count number of operations, we will observe that indeed it's going to do n log n number of comparisons. Actually, literally like n log n, not some, 27 n log n, but n log n. All right, so it's pretty good. It is awfully slow, as we shall see. Why? Anybody could explain to me why? What's wrong? Why could it be slow? Insertions, memory allocations. These are all correct answers. Rebalancing. But you see, in some sense, whatever you need to do something, you really, okay, if we think about the problem, could we do it without, okay, we have to do sort. Without sorting, you really cannot find out how many unique elements are in a sequence of integers. This is a paradoxical thing. It seems that finding unique elements is much easier operation. And of course, yes?
If we have extra memory, we could use it and do it in linear time by just having like histogram type.
Well, if you do have 2 to the 32 Extra memory, yes. But some of us are not as, rich as you are. And, I probably lie. It's probably 64-bit integer. So I was going to use this. But this is a good idea. I'm not trying to shoot you down. We will see that it's actually a very solid idea, but just not here. Sort of, in some sense, we have to figure out what is the problem. First of all, let us just dwell on it. So why do we need to sort? In some sense, it seems that finding unique elements does not require ordering. It just requires equality. Right? For example, yes?
Could you use a hash table with a load factor of 1 or something like that?
Yes, but just let us, this is not what I'm talking about right now. We can, but why couldn't we use equality?
We have to find fast whether we have this element or not. We have to optimize find.
Yes, and equality will give us what? Linear time to find. Very good. So, of course, there is an algorithm. You say, but nobody will use this algorithm. This is not so. There was a famous programming language called Common Lisp. Some of you think it was a great language. I know one such a person, at least here. And they carefully designed a bunch of algorithms which work on arbitrary sequences. And one of the algorithms was called remove duplicates. And it relied on equality. It actually would go through, n times removing things. They did not sort. They used equality. It did work. And it worked exceptionally well for most of the applications. In Lisp, you usually have a list with 5 elements. So, it works just fine. The moment you go to larger lists, things stop working. Quadratic algorithms are slow. Right? Sort of one of the amazing things which we will discover is that ordering is very important. Things which we could do with ordering cannot be effectively done just with equality. Right? Again, restating what Vitaly just said, the equality gives us linear search, while sorting gives us binary search. Binary search. That's the term. So we could find much faster. So this is why. But set does sort. It's a way of sorting. Right? But again, it's a complicated way of sorting. And here we're getting to another very, very important point. If we are going to just go by the book, we will say sorting is good as long as it does approximately or order of, well, if you know about big O, n log n operations. Well, this is good for the books. It's actually not good for our code. Because big O, for example, could have an arbitrary coefficient. It could be 50 times n log n. There could be large coefficients. And that's what happens. The effective coefficient, when we, not just in terms of number of operations, but in terms of time for this, is very, very slow. How slow? Well, we will be doing measurements together of this very problem, but let me tell you, between factor of 20 to factor of 50 on large data sets. And that is a lot. All right? So how would you solve the problem? Could we do it, could we replace it with a one-liner which will do it?
2 lines.
Okay. Okay, so tell me, what should we do?
Sort A,
And then?
and then do standard distance of begin of A, and then unique of begin of A and end of A.
Very good. Very good. So let us see. And you are, I'm sorry? Ahmed. Very good, Ahmed. I will learn, guys, but sometimes I will have to ask. So this is very good. So let us see what Ahmed suggests. He suggests that, first of all, we do not need to construct anything at all. And this is, okay, some of you will drop after the first lecture, right? That's always happens. Because you will be bored, you say this guy doesn't know anything. All true. However, before you drop, let me tell you a very simple piece of advice. So if you remember just one thing out of this course, it should be this. Two pieces of advice. The first piece of advice is whenever you can, use vector. The second piece of advice, if you cannot, find a way how you can. That is, avoid any data structures except arrays. Vector is an array, right? Sort of, you say, well, aren't there exceptions? Yes, not for you. That is, it literally, if I were Brian, and I'm clearly not, I would issue an edict that, he's allowed to issue edicts, that anybody who wants to use advanced data structure should have one-on-one with him. And explain. No. Maybe he will even get a raise. But it should be a very special occasion. Because typically advanced data structures are slower than simple data structures. And again, part of the thing which we're going to study in this course is that data structures which appear to be all right when textbook writers wrote their textbooks are no longer all right now. Computers change so much that things no longer work. Things which, and I belong to the generation of textbook writers, so I know. So let us try to see how we could do it. I mean, the first thing we could very simply do std colon sort, which will allow us. I am still doing it this incorrect way. Right? So that assures us that it's sorted. And then what we can do, and I'm not going to use distance here. Why am I not going to use distance? Since you suggested distance. Explain to me why I don't need to use it. Because these are pointers. Right, again, never use a function which is intended to use in a general case when you sit deep inside some specific case. Because also, when we say std distance, 70% of the people here don't know what it means. When we say subtract two pointers, only 30% don't know what it means. So, you always, basic rule, we always want to use the simplest possible language construct, the simplest possible thing, because we are writing for other programmers. Because, I write code, and then Paul, and happened often, will have to modify it. Right? So I have to assume that he knows nothing and use the simplest possible. He knows quite a bit more than I, but so what we need to do, we need to really use unique std unique. Thank you. Std unique, and you see this is my unique contribution to computer science. There was this great man called Ken Thompson, and he changed the spelling of unique. You know that, right? And my great contribution to computer science was to restore the spelling of unique. It's not bad. Oh, no. So unique A plus 6. What does unique do? Anybody knows? I know that you do, so let somebody else tell us. So what does unique do? Yeah, it goes through a range and sort of removes all non-unique elements, sort of returns a range of unique elements. Of course, the presupposition is that the range is sorted, the precondition. It will work if the range is not sorted either. It will just not eliminate all equal elements. The range is sorted, all equal elements sort of put together. So, and then what does it do? It returns a pointer to the element past the last element in the range. This is a standard STL convention. We'll study that. So in any case, STD unique will point to the past the last non-unique element, past the last unique element. Here, finally, I could test the new boards. So let's assume that we have 1, 1, 2, 2. What unique does, it does 1, 2, and whomever lives here doesn't matter, and returns us a pointer to this. It's actually going to be 2, 2. But, what? It in place moves things around. Right? For those of you who do not want in place, there is an algorithm called guess. 3 guesses. What is it called? Unique copy, yes. Sort of, again, sort of, because you could say, why do you need it? You could just copy and then do unique. Well, but I could do unique copy faster than doing copy and then doing unique. I don't need to move all the elements, just the unique elements. Right? We will get to that. So there is no count unique in STL. Okay, this is a very good question because we're going to get to it in 3 minutes anyways. Right? So, but because you see, Param noticed that while this is all right, it's not perfect. We don't really need to move things in place. We just need to find out how many unique elements are there. And we will work on it maybe jointly in a few minutes. Okay? So we need to do one more thing. Right? Include algorithm. Who said that? So, very good. Yes, you have to include all the algorithms in STL. Live in include called algorithm. And it was much easier when I first did STL. I had one gigantical file called stl.h. But at that time, people said it's utterly unacceptable. You have 20,000 lines of code. People cannot have includes that large. So if you think about it nowadays, it appears to be very funny. I mean, 20,000 is nothing. But that's why stl.h was replaced with gazillion little headers. And sometimes, as you will learn, I have no idea what they are. Right. As I just said. So
But we don't need set anymore, do
we don't need set. But we might need him later. So let's let's not be so greedy. After all, we're not even wasting paper here. What are we wasting? I don't even know anymore. So let's keep it. We might need both soon. So, but we need to be sure that it works. Do we? Do we? You are? And in C you would need to divide? No. No, not in C. Maybe in BCPL. Have you tried BCPL? In C, pointers are typed. Yes, so, you know, you have to, I mean, when you take a difference between two pointers of type T, you get the number of objects of type T between these two pointers, not the number of bytes. If you need number of bytes, then you need to multiply. All right? So, but it's, again, it's very good, guys. Do not, sometimes I'm going to be a little bit, you know, teasing you, but we have to get it all because nobody really, nowadays we got to a point where nobody teaches programming. Right? Because for why? Because no professor of computer science has any idea how to program. I mean, unless, I mean, there's, like at Stanford, there's one guy who knows, but he's an emeritus. You might know whom I'm talking about. Huh? So they thought he wasn't good enough, so he had to retire. Right? But most of them, well, they might have some knowledge of how to program and, you know, standard ML or things like that, but nothing like that. Nothing like that. So what happens is that people come from schools, all kinds of schools. They never learned how to program. And this is, now I'm going to give a speech, which I actually planned to give in the beginning of the course. But now it's a very, very good time for that. And let me tell you, start with, since we were talking about great programmers, we mentioned Ken Thompson. And you know who Ken Thompson is? What did he do? Yes, yes. So he did many wonderful things. Sort of he, in some sense, probably more than any programmer, influenced the programming style which we have right now. Sort of while he did not invent C, that was done by his friend Dennis Ritchie, the programming style which underlies C, dealing with pointers, knowing how pointers are subtracted and stuff like that, that all comes from Ken Thompson. And because believe it or not, best and brightest at that time were heavily on the march to get rid of pointers. There was absolutely brilliant people who would give Turing Award speeches. Tony Hoare is the case in point, saying that pointers have to be abolished. Right? So the idea was that pointers were these illegitimate things. And language designers were fully convinced that even if you provide pointers, nobody would call them pointers, they would call them something like access types. They have to prohibit operations like that. You could never subtract pointers. Right? Like Niklaus Wirth, the designer of Pascal, was very certain that, you know, you should never allow subtraction between pointers. So and it's due to Ken greatly that we still have it, at least in some languages. I know that our Java friends do not believe in pointers and subtraction of pointers, but pointers are still at least partially with us. And so, but Ken was absolutely a great man in many respects. His career started not with Unix, but with, when he was freshly out of school, coming up with a brilliant practical algorithm for matching regular expressions. Every time you write grep or something like that, you're most likely exercising code written by Ken in the late 60s. Right? Sort of all this reliance on regular expressions in practice, because regular expressions were invented, believe it or not, by theoreticians, ivory tower guys, specifically Stephen Kleene, who was a logician. So Ken made them practical. Right? Then he did Unix. this totally brilliant operating system on which we all rely. Right? I mean, all of us, one shape or form, livelihoods come from CAN. It used to be that, do you remember what fortune cookie program was? So in the original Bell Labs thing, one of the fortune cookies was, it all Ken's fault. And we have to remember, it's all Ken's fault, I mean, without him. After he does that, just to demonstrate that he can do anything, and he can, at least he could in the past, he decides to show people how to play computer chess. Mind that at that point, as far as I know, he barely knew the moves. And there was a total dominance by a Russian chess-playing program, Kaisa. And 2 or 3 years, he builds this specialized hardware, totally revolutionizes the approach to chess playing. And of course, nobody remembers what Kaisa was. Sort of, he's a guy like that. He could enter a new field, totally new field, and do something beyond, I mean, not just world class, but beyond world class in a short period of time. So in 1984, he was given a Turing Award. You know what Turing Award is, yes? That's something you should aspire. Every programmer at A9, do you support me? Sure. Yes, Brian supports me. Every programmer at A9 should aspire to get Turing Award, like Ken. And he got it in 84. It was shared with Dennis. And he gave a beautiful speech, Turing Award lecture, which I highly recommend that you read, called Reflections on Trusting Trust, which talks about many things, but I'll use just one little episode in the beginning, which is very important from my point of view. He says that he was very blessed with collaborators, specifically with Dennis Ritchie. And Dennis was a genius, first class, of course. And then, this is mine. So then he continues that when, during many years of their collaboration, not once they would attempt to do the same thing, both of them. They had this good sense to work on complementary things. Except once, then, as he says, both of them needed to write an assembly program with about 20 lines of code. And, continues Ken, I checked. It was character by character identical. So it sounds as this mystical thing, right? The two people. This is Vulcan mind melt or something, yes? But there is something profound there, and I actually think that it's less amazing than Ken makes it be. And that is a central point of what I'm trying to teach here. You see, I actually had such mind melt with several of my colleagues after we worked together for a while. For example, it's literally true that when Dave Master and I, some of you might have heard, I have a friend called Dave Master, some of you met him, that when we were working together, we were working long distance, and sometimes we were not as good as Ken and Dennis. We would write the same thing. It was invariably character by character identical, right? When I was working with Paul, by the time, right now, sort of, I have been looking at some of the code he wrote without my supervision recently. He put some stuff in our book website, which I actually never saw. I could write this code, character by character, identical. I didn't, but I would. It's literally the same code. So I claim that in some sense, if we are really sort of turning programming into professional discipline, then the story of Ken and Dennis will not be a miracle. We should be writing basic code, character by character, identical. And in some sense, imagine how wonderful it would be if you could understand what he wrote. Because right now, I mean, if you look, it might not be in visual search, or might not be true in other parts of A9. But if you look at the core search engine, there is, let me put it, a wide variety of programming styles. Basically, you couldn't make head or tail at any given point. As Hernan told me last week, maybe this week, that there is this comment which is 1 page long, which he spent months trying to understand. Quoting correctly. Failing to understand. Right. So never mind the code. It wasn't fast hash map. Yes. It was the comment he is referring to. Anil figured out. Anil understands. So which now you could understand why Anil is such an important guy here. He's the only guy who could understand the comment. So no, but it's a typical thing. So in some sense, part of what I am trying to do here is to start discussing these little things. Eventually we will even discuss how do we name variables. And say, why is it important? Well, it is important. We want to get to a point where everybody writes a consistent code, recognizable code. Right? Do I have your support on that? Yeah. I have full management support on that. Total. See? No Hungarian, and we will not use Hungarian. Yes. So it's his best friend who invented it. Oh, really? Yeah. But now he's flying to the moon, so I'm marrying Swedish countesses. It's a good thing. He moved on beyond. Yes. So this is why I want to go slow and develop so that we all agree. So everybody understand what's going on here? Right? So now, what we need to do, now I have to think. I covered roughly 3% of what I was planning to cover in this lecture, but that's all right. That's all right. We are not in a hurry. So what we're going to do is the following thing. Let me just suggest my plan for where we're going to go. We're almost at the lab time. And during the lab time, I want to get us to a point where we start learning how to measure things. And when we measure algorithms, there are 2 ways we could measure, 2 important ways. I'm not going to ask you because this is like, I have 2 things in my pockets. What are they? No, we're not going to do that. So the 2 important things you could measure is you could measure operation counts. Right? This is something, again, there is a great book all of you should have and all of you should aspire to read. But actual reading, that we don't know. Actually, you should. You know the book I'm referring to? There's only one book like that in computer science. Art of Computer Programming, written by Donald Knuth. Right? It's a very imperfect book, but it's the greatest book we got. And in some sense, one of the things which I want to convince you is that we want to be professionals, and as professionals, we want to sort of have certain things on our bookshelves, even if we don't read them. Like, lawyers, you go, they have all this legal stuff. They don't know anything about what's inside, but they know they have to put it on the shelves. So we at least have to aspire to the same level of professionalism. We put Knuth on the shelf. So, and when we start reading Knuth, we observe that even very long time ago, Knuth started doing measuring operations. That is, when he would describe an algorithm, he would not just say big O. That came later, in spite of the fact that Knuth was the guy who introduced big O into analysis of algorithms. But in his book, he would carefully annotate how many you could come in. Just push them, push them. Guys, there are chairs. There's one chair next to Bert, I see there. Is there a chair next to Bert? And there's a chair next to Param, I think. And there is next to Sergey there. You have to be assertive. We need to buy a bigger building. So, okay. So one thing we need to do is to learn to count operations. And the second thing which we want to do is to learn to measure time. And in some sense, both of them are important. Because if you count operations, you could have, if you like, an analysis of algorithm in terms of abstract operation, not depending on a specific type. Which is very good, we have to have that. But then you have to have it also times for specific commonly used types. Right? So these is two things which we need to do. And what we, sort of our goal is to be able to measure doing this thing with set and doing this thing with sort. Before we go to that, however, I know there is there a pizza waiting? Is there pizza there? Is there pizza outside? No, it's probably there.
I see cookies.
Do you see cookies? Sandwiches, good, good. So there should be enough sandwiches for everyone, so you don't have to. So, but before we go and start the lab, figuring out how we do the counts, I have to ask you one more question. So if set is so bad, why is it in the standard?
Define that.
If it's slower than straight sort.
Maybe it's good for something else.
Like what?
Small sets for determining the presence of an element.
Dictionaries. Insertion.
All of that, think about it. If you do insertions, you typically, for example, in 90%, 99% of the cases, you do all of your insertions, then you do searches. Then you do not need a set. So set is a very specific data structure which is needed only when you have a very specific workload, when you don't have a typical build use, as we always have in the search engine. If you have a thing which sort of grows and shrinks constantly dynamically, then you have to have a set. If you have a thing which it provides, it's a very powerful thing. If you need a thing which does not move things around, because as long as something gets into a set, as long as it's not erased, the pointer is fixed. If Ryan is in the set, he's sitting in this chair, for as long as he's in this set, he will not move from this chair. You could find him in constant time. You could store a pointer to Ryan someplace and find him. It's a very useful thing, except most people do not use set for that. Sort of, again, what we need to understand, and we'll get, I mean, toward the end of the course, we'll be talking about sort of different uses of data structures, is that in most cases, sort of, this is a very sad thing, which that, you know, when let's even forget about 8.9. I remember when I joined Adobe, Paul was there. What do? I go and start answering questions because people say, oh, Alex is here, so whenever we have a problem with STL, we'll ask him questions. And people come day after day after day showing me the examples of use of STL. The most common thing, they'll have something like map of maps. Right? And you sit there and you wonder. I mean, before STL, nobody in his right mind would dare to say, I'm going to have a self-balancing tree, which at every node has self-balancing tree. Right? Why they wouldn't think? Because it will take them 5 years to implement it. Because even fast hash map does not allow you to have fast hash map of fast hash maps. STL, and we shall see it's one of its strong points, makes it all trivial. You could not just have map of maps, you could have map of map of map of maps of vectors of list of maps of sets, however deep, and in one line. Will it work? Yes, for some definition of word, work. Right? Will it be fast? No, absolutely not. I mean, it cannot be fast because you have this enormous complex stuff. Its complexity is hidden, but it's still there. So you have to understand that the miracles are not possible. If you ask somebody to create a very complex data structure, that's what you're going to get. You're going to get a very complex data structure. Right? And whatever people were saying before, you're going to get problems with node allocations. You're going to get problem with rebalancing. You're going to get problem with whatever these advanced data structures do. And these problems are going to get worse and worse and worse. And then, especially, you're going to get a cache miss on every step through the set. Right? And as our computers become faster and faster and faster, they're getting slow and slow and slower, meaning that going to the main memory is really very slow. So as we will discover, you want to have locality of reference. You want all your data you're working on in the local cache. If you have a huge set or map, it's not going to be like so. You're going to have misses on every step through the data structure. That's not good. So again, what our task right now, we'll go grab sandwiches. And our task will try to write together, but you will be writing and I'll be sort of guiding, an infrastructure for counting operations. All right? Sandwiches. You're welcome.